Other people might join, but let's get started. It's a little bit early in the morning. We'll start slow. As I was saying, I only have 30 slides, because there's like a title slide and a reference slide. So please ask questions. Yeah, so it's not going to be a very technical lecture, hopefully. So I'll talk about this paper a little bit, maybe 10 slides from now. But let me kind of give you more of a background motivation for this project, but also maybe give you some ideas how to proceed with your research. Sounds good? Okay. So this is one of my favorite recent paper. Not really an I/O paper. This is the author, Van Wienan, and then 3 other people. The Superstar paper, right? So, what a lot of macro and labor people have documented over the last 30 years is this, massive reallocation in the economy, and characterized, macro people looked at that and say, well, the labor share is going down across many industries. And a lot of that decline in the labor share. Now, from an IO perspective, I don't really care that much about the labor share, but what this is telling me is that there's massive decline in variable cost, right? So the labor share is just a proxy for variable cost. And what these papers have shown is that if you look across industries, you see more or less the same pattern. The variable cost is declining. And when you look at the decomposition of why we see the average labor cost declining, so this is coming from the L.A. Pecos paper. Peril wrote this paper here, so felt like I should be pointing this out. So what the L.A. Pecos, how do you decompose a growth rate or in this case the decline in the labor share? So S is the weighted average labor share across firms in a given industry, okay? And Ole Pecos decomposition is just, this is defined as just the weighted average of the labor share of each firm in the industry. This is their, let's say, revenue share or market share in the industry. And Ole Pecos is just a decomposition by saying, well, I can decompose this into an unweighted average, productivity or in this case labor share, and a covariance term. Like, is it the case that the larger firm have lower productivity or higher productivity and vice versa, right? So when we talk about reallocation in an industry, we're looking at this term. And so if this term is positive in this particular case, well, so we're expecting negative in this case that larger firms have lower variable cost, right? And there's a dynamic version of that decomposition here where you can look at changes in each of these terms to look across very long time periods, which is what the author paper does. Over these 20 years, and you can look at changes in the labor share or changes in productivity over time and decompose it again by looking at whether the unweighted average among incumbent firms present in both time periods have been declining, whether there's reallocation, essentially changes in this covariance, and then reallocation through entry and exit. Is it the case that high variable cost firms are exiting and replaced by entrants that have low variable cost? And when these colors are telling you, I highlighted retail because I'm mostly going to talk about retail. Well, what this is saying is that in retail you do see, like in other sectors, decline in variable cost. But what's interesting here in retail is that most of this is due to a reallocation. Most of this is due to a reallocation between essentially firms that are growing really, really fast are also the ones that experience the largest decline in the labor share. Now, the author paper talks about that as a superstar effect, okay? And now, you can do that across industries, and the same thing is true across many industries. So the takeaway, at least from IO economists, is that when you look at this kind of fairly long time period of 30 years, most industries have experienced very important secular trends. Okay, so this reallocation toward very big firms that have low costs means that when you look at concentration in industries, concentration in most industries have gone up quite a bit. Okay, now it doesn't mean that market power has gone up. So there's a rival paper of this, the ECOUT and the Locher paper that says, well, though market power has gone up, I'm not going to say that here. And the story I'm going to talk about in the industries I'm looking at today is mostly about technology, not so much market power. But the fact is that across most industries, you see these very big non-secular trends that has been associated with declining variable costs and a reallocation from high-cost firm to low-cost firm. Okay. Yeah.
Just to understand the mechanics of the decomposition.
Yeah.
Like if you just have a steady state.
Yep.
Where a cohort is born less selected, and then it gradually grows more selected, and we have like new cohorts coming in, and they're dying out, like standard clinic cordon stuff or Oppenheim stuff. And the selection is that you're moving resources from less productive to more productive firms.
Yep.
And more productive firms are characterized by a higher labor productivity,
yep.
lower labor share. This isn't like I'm going to find a reallocation.
Of course, no. And so yeah.
Is this a secular trend?
No.
Feature of the
Correct. No. So if you were in a steady state, the weighted average would stay the same across these 30 years. But within an industry, so what Rasmus is talking about is, those classic industry dynamic models in IO and macro, like the Oppenheim model, for instance, that talks about a reallocation mechanism, right? Where, good firms are good for 1 year, and then eventually productivity can go down, and you're replaced by other firms. Now, in those models, you're thinking about a steady state, so all of these aggregate statistics are constant, but you still have a lot of reallocation coming from entry and exit and coming from within industry comparison. What these papers are showing is that, wait, if you look across these 20 years or 30 years, the aggregate statistic is changing a lot, right? In Oppenheim, in these traditional industry, or Ericsson Pekis that we talked about, even though the industry might be fluctuating from year to year, there's no secular trend. Right, we're looking at a market structure that are fairly constant, like Ariel was talking about, a recurrent class, right? And so, when we analyze those empirical models, we think about models. Those are good models that predict industries that are very much stationary, where on average entry and exit balance out, and the firm size distribution is more or less constant. But what these papers are showing is that, that might be true if you look at a fairly short time period. But if you look at the last 30 years, that's not the right model. Okay, we need to think about these non-secular trends because a lot of the dynamic in these industries is causing market structure and concentration, firm size distribution to change a lot.
So the decomposition you're talking about here is the decomposition of the aggregate change.
Exactly. Yeah.
Not the regular decomposition that we know that also results in a large reallocation component.
Well, I think it's the same, but the aggregate, if I do an aggregate decomposition in Oppenheim, there will be positive and negative terms, but the aggregate number would stay the same. If I do the same, sorry. When you do like a typical Oppenheim decomposition, you're going to look at this number. Okay, but across many sites, this aggregate statistic would not change in an Oppenheim model. Okay. So again, the author paper, and you can come up with different stories, but the author paper thinks about this as technology changing. Okay, so there's new technologies. Think about winner-to-take-all technologies, or technologies that have big economies of scale. And so some firms are going to be adopting those technologies, and those firms will grow much faster, experience decrease in long-term average cost, eventually dominate their industries, and that will give rise to concentration. Now, the examples I'm going to give you on retail, the Walmart and Amazon example fit very well there because that's, we've experienced massive increase in concentration in those two sectors, mostly driven by technology. Okay. Now, across industries, it's not always the same story, right? And Dean is not here, but Dean loves to show a similar graph where he looks at banking. The banking industry went from not very concentrated to very concentrated. A little bit is technology, but a lot of it is deregulation, right? In some industries, it's trade. We open up trade, and then suddenly, it gives rise to more concentration or easier access to inputs. But I'm focusing on technology here. Now, there's not a ton of research in IO thinking about these non-secular trends. because it's really hard to do dynamics, right? But we'll try to make a little bit of progress here. But this is a big, important avenue for our economists because it's in some ways it's more interesting dynamics than just the typical entry and exit where one firm replaces a bad firm, right? Okay. So what happened in retail? So this is the fusion of Walmart. I'll talk a bit about the story for Amazon, which is a little bit different, but also related with logistics. So the big innovation in Walmart and the big box kind of revolution in retail is this change from the traditional distribution chain for retail, which I put above, to kind of what I call the big box model of distribution. Okay, so the traditional model for how retailers acquire goods is you have manufacturers upstream, right? They ship good to an intermediary, call it a wholesaler or distributor. This could be an importer, right? And then that wholesaler, give it to a distributor who's going to ship the good, and all of that is separated along these 4 levels. Okay, and then the retail distributors, going to be more local, and then send it to the retailer. Now, in the big box model, what Walmart did is very different. So Walmart, they said, okay, I'm going to be a retailer, but I'm also going to be my own distributor. So Walmart essentially vertically integrated upstream, okay, and it developed their own network of distribution, their own trucks, their own distribution center, and effectively forced the manufacturers to become wholesaler and to ship directly to the warehouse of Walmart, okay? And so that puts a lot of, a higher cost to become a Walmart firm, a Walmart distributor, because a Walmart supplier, because you really have to ship the good directly to Walmart, but that cuts two part of the chain, okay? And by vertically integrating, Walmart was able, so big fixed cost investment, but was able to eliminate all sorts of costs. Like you think about double markup problems and inefficiencies of sharing the distribution asset. And so that's where a lot of the cost savings from that model. So now there's limitations of this, right? So what you want to do because distribution is known to have big economies of scale, so you cannot have too many varieties if you're going to do that. So you want to have high volume products and not too many products, otherwise you kind of destroy the benefit of vertical integration. So what Walmart did, if you go to Walmart, of course, you see one brand of Kleenex, you see one brand of toilet paper, and so you're not going to see a lot of variety. And the point is to have goods kind of rotating very fast on the shelves and benefit from economies of scale and distribution. Okay. Okay. So this is all coming from the Tom Holmes paper. And when Tom used to present that paper, he actually had video. I didn't put the video. But you can see the expansion. So the trade-off that Tom focuses us on this paper is the trade-off between realizing those economies of scale. So, because we're talking about distribution, we're going to call this economies of density. But think of it as, in an aggregate sense, it's just economies of scale for that Walmart has. And so the trade-off here is, so let's say that the square dots are the distribution center that Walmart put, and the dots are little stores, right? So to realize those economies of density, I want to be close to the distribution center. Because if I'm too far, then the truck is not, it's going to have to travel a lot. Now, the other thing that is a bit more subtle is when you have a big distribution center, what the logistic companies are doing is that they take the truck, right, and then the same truck will deliver goods to multiple stores. So there's a lot of density. That's why we call it the economies of density. There's a lot of densities of stores nearby. The truck never travels empty, and so you can use the same truck to kind of go back and forth. The truck is always on the road, effectively, deliver goods from the distribution centers to the stores. If there's only one store, then the trucks are idle, a lot more frequently, and so you're not using the asset very much. Okay, so that's why you want to be, you want to pile up stores nearby distribution centers to realize those economies of density. But the other side of the trade-off is that if you keep piling stores nearby, at some point they're going to cannibalize each other, right? And they're not going to generate the volume that you need, okay? And so what this map is telling you is, as demand was increasing, and Walmart becoming more and more successful, Walmart kept branched out of the area. So they start in the center, and then realize the economies of density nearby. Then I maxed out on these economies of densities and I open in the different areas. Now the volume is not going to be there, but eventually I'll have enough volume and to generate the economies of density, and then I'll move out again. And that's kind of the propagation map that he was studying. Now, it's a very different type of dynamic data that what we've covered, okay? But what the goal of that paper and our paper on Amazon is to kind of look at these diffusion patterns to infer something about the economies of density. Okay, so I want to use the non-stationarity of my data to infer something about the cost saving, this trade-off between density and cannibalization. Sounds good? Okay. So here's the model. I'll briefly talk about this, and the model is fairly similar to what we're going to talk about in the Amazon paper. So the model is, as I was mentioning, we're trying to model the diffusion, okay, of where to place the stores. It's not a model about how many stores to open, okay? So we're going to take that as given, take the number of stores as given, and only try to understand where to place those stores, okay? So, I mean, I'm not saying that the number of stores is exogenous. The reality is that you're maximizing both on number of stores and the location, but given the number of stores, there's still an optimization problem, right? And so I'm going to look at that optimization problem, where to place the stores, okay? So I was in Europe earlier this summer, and in Europe and I/O, people do theory. And there was a competition, effectively. Every talk, author were saying, well, this is the simplest model of the conference. And then the second talk was, now, this is the simplest model of the conference. Now, this is this. And it was like this ramping up of how simple the model can be. So in North America, we do more complicated models, but we tell more clunky stories, I guess. Now, the reason I say this is that this is by far the more complicated model of the conference, okay? But it's also going to be the strongest assumption. Okay, so complicated models, you have to make very simple assumptions. Okay, so
Didn't Tom have a version of this that was an adaptation of the Cordon to Walmart?
he might have. I think he has other papers that have these kind of features, but not this paper for sure. Not.
This looks different.
Yeah.
I think he found that the Cordon level dynamics was quite successful in the Walmart.
It's possible. It's possible, but it probably not looking at this level of geography. Yeah, it's probably simpler. Probably simpler. Okay, but here are my two very strong assumptions. Okay, I'm going to assume that at the beginning of time, when the Walmart guy, what was the name of the Walmart guy? Sam something, right? Sam Walton. Good. Okay, so Sam woke up in 1972, okay, had perfect foresight about where the demand is going to be from, 70 to 2012, right? And was able to kind of mastermind the path of diffusion, thinking perfectly about the future. Okay, so cannot be a stronger assumption than that, right? Second assumption is that there's no unobserved preference shocks. Now, I'm going to relax that when I get to the econometrics, but just for now, let's pretend there's no unobserved shocks. So the model is completely deterministic, okay? And so the value function, if you will, is this. So what I'm choosing A here is, I'm at the beginning of time, I'm looking in the future, and I'm given the number of stores I want to open in each year. A here is, essentially a network, right? So matrix of zeros and one, where to place the stores. Okay, so there's a lot of potential locations that I can place the store. Right? It's continuous in some ways, right? So, and then A is that. So it's the sequence of where to place the stores, and I'm maximizing my value function this. So there's two types of stores here, the regular Walmart and the superstore, but forget about that. That's super important. And then the key parameters I care about, so those parameter pi, you can estimate them using revenue data. That's where the cannibalization is going to come in, right? So the demand, how many stores are in a given area will affect the demand, will affect the profit, okay? So that's where that thing is. The economies of density is coming from the fixed cost. So this is the story I was telling you, when you place a store in a given area, right? The trucks will continuously deliver the good. Okay, so the delivery cost is not a variable cost, it's a fixed cost. The truck is always on the road going back and forth, okay? And so the more stores are there around, you can share that fixed cost, okay? And that's this guy here. Okay, so this is the density parameter there. And the other one is just like, okay, it might be more expensive to build a Walmart downtown New York, and that's what these parameters are giving us. Okay. Okay. Now, again, the model is too complicated to solve. Okay. There's a few reasons for this. One is the choice set is enormous, right? But the other big reason is that it's a non-stationary model, and I have no idea where a Walmart is going. It's going to be probably more true for Amazon because we're only looking at the first 15 years of Amazon. But I don't know where Walmart is going. And then there's an option value of building this network. Walmart is probably thinking about competing with Kmart, competing with other firms down the road. So there's a big option value of investing in a good network. Okay, the model is completely silent. That's implicit in the value function, but I don't have a model of what's happening down the road. Okay. And I don't want, because the model is non-stationary, I don't want to take a stand about what is this option value in the future. Okay? So instead, we're going to try to bypass this calculation of the value function and taking a stand on what the future is. Okay? By using a bounding idea to bound the fixed cost without having to compute the problem. Okay? So for a second, just to give you an insight on the bounding exercise, ignore the dynamic for a second. Yeah, go ahead.
Just clarifying, I'm trying to read do you mind going back a slide?
Yeah.
I'm trying to read your F.
Mm-hmm.
How are the different stores interacting with each other in the network? Does it matter that I'm opening a store next to another store? Does that help me?
Yeah, so that's in the pie here. So if there's a lot of store near me, then the demand is going to be smaller. So the demand at a given store is a negative function. Yeah. And then this is the proximity to the nearby delivery centers.
So it's the distribution center that's the key.
That's what creates.
And it's the other stores that cannibalize.
Yeah, so exactly. The negative thing is, so everybody wants to be very close to existing delivery centers because the truck is going to be on the road all the time. So if you're far away, that fixed cost of having the truck on the road all the time is going to be very high. But if you're close to a distribution center, that's a lower fixed cost.
And is there in this problem a distribution center creation?
No, so we're going to take as given the distribution centers.
Okay.
The point here is I want to quantify this parameter. That's the main point of this paper. Yep.
Any cost of entry or?
There's a fixed. Well, you can think of that as a. No, there's no sunk cost. There's no sunk cost. Everything is I mean, there's probably is, but it's going to be differentiated out from the way we're going to do this. Sounds good. Now it's a very incomplete model, as you'll see. So all of these. For example, like what Bertil is saying is, let's say there's a sunk cost of entering, that's not captured here, right? But the way we're going to do this, I'll tell you in a second. Okay, but just think about the static model for a second. How does bounding help me? Okay, so think about this trade-off, cannibalization versus proximity to the network. Okay. So if I see a firm or a store entering early in a state, I'm the only one in the state, high demand, no cannibalization. Okay? Compare that to a store that enters later. Compare that to a store that enters in a crowded space already. Okay? So if I enter early in a state, I increase my profit, but I'm incurring higher distance cost. Sounds good? Now think about another decision of entering late in a state, meaning low profit. So I'm already entering in a crowded area, but I have lower distance costs. Okay, so I have these two new things. Okay, so let's say that I see in the data A star is my optimal action. Okay, and I'm comparing A star with something that I could have chosen, A prime. Okay, that leads to higher profit. That this leads to higher profit than this, but the distance is larger. Okay, so if you arrange this, so when I see Walmart opening early, it did that because they want to have higher profit at the expense of higher distance. That gives me an upper bound on the travel cost, on the shipping cost. Okay. Now the same thing if you can find another alternative where you did the opposite, where you decide to enter in a crowded space, that gives me a lower bound on the travel cost, on the shipping cost. Okay, so that captures the trade-off. So if I can find many of these rejected options, right, that kind of shift the trade-off in different directions, then I can create informative bounds on the shipping cost. Okay, so that's the logic of the estimation approach that we're going to use. In a dynamic context, it's a little bit more ugly, okay, because if I compare a particular decision with another decision, I might need to worry about the option value being different between those two things. And remember, I don't want to think about the continuation value, okay? Right? So if two alternatives lead to different continuation value in the future, I need to know the impact of my decision on the continuation value, and I cannot do that if I don't know the value function, okay? So here, Tom was using something that Peter and Bob were talking about earlier. So this, now I'm blanking on the terminology that Peter was using. Finite dependence, right? You heard that term before? Good, okay. So finite dependence. So in this context, what we want to do is we want to compare two alternatives, okay, where the continuation value will cancel out. We don't need to calculate, we don't need to worry about the continuation value. So where's that, and this is where the perfect foresight is very helpful, okay? So I'm going to compare two networks. A star is the chosen network, and A prime is very similar to A star, except that they perturb the entry date of two stores, okay? So same network, okay? It's just like, you know, I open in Arizona first and then Texas later, let's say. So that's A star, and then I'm gonna swap these two and say, no, you enter in Texas first and then Arizona later. Okay? Does that make sense? So that's the only difference between A star and A prime, okay? And T1 here is the entry date of the later, let's say the Texas one. And then T0 is the entry date of the first swap, the first store I'm swapping, okay? So when you look at the value function I showed you before, if I want to compare the difference in the value function between those two options, okay, everything that comes after the second entry is common, right? Yes, I know all of that. I'm conditioning on what, I'm optimizing on those, but I'm not touching those, right? So by doing this.
Well, you're optimizing given those.
Yeah, so I'm optimizing given those, okay? And so given all of these assumptions, the difference in the value function between two networks, right, is only function of the discounted profit during those two anterior periods between T0 and T1. Sounds good? That's beautiful, no? Okay. And that has to be positive, right? If, again, no unobserved heterogeneity, nothing, that has to be positive, okay? Now, in the Walmart case, it's great because Walmart opened, you know, I want to say a bad word, a lot of stores. Right? And so there's a lot of swaps that I can take to calculate this, okay? Now, because the fixed cost is linear, right, and I'm assuming I know the profit, this is actually a linear inequality because the profit is linear and the value functions are linear in the parameters. Okay, so I can calculate y. Y is the difference in variable profits between these two alternatives, right? And x is just the difference in distance between these two alternatives. The way, discounted sum of these two things. Sounds good? Okay.
I guess if the entry cost and sunk cost would be the same.
Exactly, exactly. So all of there's other components of entry cost that are absorbed by this comparison. So as long as the sunk cost of entering is the same between these two swaps, then it just cancels out. Okay. So it's a very incomplete model. That's what I meant to say earlier. Is that by doing this comparison, you're eliminating a lot of components of fixed costs that are common across the stores. Okay. Okay. Now, in principle, there's a lot of inequalities that you could have chosen that would estimate those, like not opening at all this store, right, or entering in a location that I don't see, right. But the problem is that those swaps require you to know the continuation value because you don't have the finite dependence anymore. Okay, so you can identify more stuff, but you need to take a stand on where Walmart is going. Yep. No. No, in fact, if you do yeah, there's kind of a trade-off here because if you do too close to each other, maybe when Walmart decide those two stores, they really talked about this simultaneously, and the timing is Walmart didn't really think about this intertemporal trade-off. If you take them too far apart, then the model is probably wrong. Like the perfect foresight assumption kind of, maybe Walmart was not really thinking about those two as substitutes. So you're not using all, in this example, in the Walmart case, you're not using all the possible swaps. You're trying to use kind of similar areas in time, but not too close. You can look at the paper, but he's selecting the swaps carefully. Okay, now let's talk about Amazon a bit. So Amazon main innovation is also on the logistic front. So why Amazon has grown up so much is because Amazon built a vertical integration strategy very similar to Walmart. Okay, so this is a Wall Street Journal article, and what that kind of idea brings the idea that what Amazon is doing is that over time it controls more and more steps in the distribution. Okay, and our study ends in 2018. But if you look at what happened between 2018 and today, it's even more because you see now the Amazon employees coming to you, okay? And so they're really controlling the whole supply chain from the boats from China, right? Bring the goods to the store, the trucks on the street. Okay. Now the concentration has risen quite a bit. Okay. So on the left you see the market share of Amazon. So nowadays, about half of your orders that you buy online is coming through Amazon. And the concentration among online retail transactions has risen quite significantly as a result. Okay. Okay, so this is kind of summarizing what I was saying, this vertical integration strategy. So we're looking at 2006 to 2018. Yeah, sorry. I think we are using a little bit the very beginning. What Amazon did at the beginning, like Wayfair, like other online retailers, was to open a relatively small number of distribution centers and then relying on FedEx and UPS. Now, those guys have well-developed hub and spoke distribution centers, the distribution networks that can take a box, and ship it to you in a day or two without a problem. So it's really easy to use the hub and spoke network of UPS and guarantee 2D shipping to anybody in the US. Okay? But it's very expensive to do that because you're relying on third-party shippers. Everybody's taking a small markup on each of these things. And those networks are not devoted exclusively to Amazon. So when there's a bottleneck, FedEx is going to jack up the price and charge very high shipping costs. So what Amazon did instead is, slowly but surely, expand its network of distribution centers to reduce its reliance on third-party shippers. Okay, so it went from 5 to 32. 5 states to 32 states, over 100 facilities in 2018. The other thing that, so this is kind of relying on, when you think about the trip, there's a first leg, you take the box, you go to the hub and spoke network of UPS, and then there's a last leg to you. The next thing that Amazon did is to integrate in the sortation component. Okay, so these are called sortation centers. Those are downstream facilities that tend to be located very close to fulfillment centers. And what it does is that there's a truck that goes from Amazon's fulfillment center, almost continuously taking box to the sortation centers. And what the sortation center does is that it takes all the boxes, organize it by zip code. And then Amazon wrote a really long-term contract, a very profitable long-term contract with USPS, where USPS just goes to the Amazon sortation centers, take the box that are organized already by zip code, and then ship it to you. Okay. Now the traditional model is that USPS has a sortation in-house, and so by signing this contract, Amazon said, "No, I'm going to do part of what you did." Okay, and I'm only going to rely on your, shippers, the delivery people, to do the last mile. Okay, and then later on, as I said, after 2018, Amazon started opening distribution centers as our delivery centers, and fully vertically integrated, and kind of ditched the reliance on USPS. Yep.
So you're going to think about the fulfillment centers as distribution centers and the sortation centers as the stores.
Yeah, you can think of it a little bit like that, yeah. I mean, the stores, I guess, would be the very last mile that I'm not going to talk about in this paper, but yes.
But in terms of strategy, how to think about the
Yeah.
network expansion
Yeah.
and stuff.
So in that sense, that's the similarity with Walmart.
So I guess the point of Tom's, when he was showing these graphs,
Yep.
there was also a clear pattern that the distribution centers, they didn't seem like they were just getting randomly placed in the country. They were sort of spreading out from
Yeah.
where the existing network is. And so you could sort of see that you're placing a store, the stores are getting further and further away from an existing distribution center, then a new distribution center shows up. The further periphery stores begin to get supplied by the new distribution center.
Yeah.
There's a reason for the new distribution center that isn't, it's taking over part of the load of the existing stores. And so it's not random where the new distribution centers show up.
Yeah.
And I'm wondering, like, in that limited finite state dependence argument, if you're beginning to think about the distribution centers as being dynamically placed as a function of where your current stores are,
Mm-hmm.
it's no longer obvious that you have the finite dependence if you're beginning to change the location of the stores.
Well, I mean, so our setting is going to be a bit different than that, because we're not going to have those facilities that are fixed. But what Tom would argue is, because you're assuming perfect foresight and you're assuming no unobserved, no shocks, you can always break. So I agree with you that the location where you place the distribution center is endogenous, and you're maximizing on both. But because of these assumptions, you can always break the maximization problem as an Euler maximization, where you're maximizing on where to invest the the very top layer, and in condition on those, maximizing where to put the stores.
Yeah, I guess what you want to do when you're breaking that up is you don't want to change the timing of when you place a new distribution
Right.
center, right?
That's right.
I think it could come up with a change in the
What you would like to.
where I would like to open the distribution center sooner.
That's possible, but I guess, yeah, I would need to think more about it. I feel like the perfect foresight and the no uncertainty really helps you, because there's no surprise. But anyway, but our problem is going to be different from that. So the trade-off is quite. Yeah, you had a question. Absolutely, yes.
So if we go back to the Walmart example,
Yep.
the way to rationalize why Walmart doesn't have a dollar store version of their stores is just because it's always going to be not the most optimal profit maximizing strategy to start building Walmart dollar stores.
Mm-hmm. That's right. That's right. Yeah. I mean, in the Walmart case, what we're assuming is that we know where the demand is growing, the market size is growing. We know exactly where the demand is in every county, and we can perfectly forecast that growth. Okay, so that's kind of similar here. Is that there's going to be demand across counties for online retail, and Amazon sat down in '99 and kind of forecast that, and those forecasts were correct. Okay, now this is the style. You'll see I'm going to add a residual to this, so it's I'm not going to literally use that as an estimator. Yeah.
I may be misunderstanding, but I guess just the perfect foresight also include then that they're expecting like sellers on the marketplace to use fulfillment by Amazon and not fulfillment by seller, and they're like perfectly predicting.
That's right. That's right. Yes, absolutely. And this is really important. So, I mean, let me show you the model a bit, and we can maybe talk about this offline afterwards. Okay, so the trade-off that Amazon faces, as I said, is a bit different from Walmart. Increasing density here means, again, initially you piled up warehouses in Kentucky. That's what Amazon did. Okay, there were like 3 or 4 warehouses in Kentucky, and then Seattle, that was pretty much it. Okay, and you did that because you want to go on the hub and spoke. You want to be as close as possible to the hub and spoke network of UPS. Okay, that's not very dense. That's very concentrated. So what Amazon did over time is to kind of spread out and locate closer to where demand is. That's what I'm going to mean by density. So unlike in the Walmart case where it was closer to distribution centers, here you want to be located closer to consumers. You want to decentralize your network and be closer to consumers. Okay. So when you do this, the benefit of this is that you're not relying as much on third-party shippers. If you're closer to consumers, okay, the manufacturers will ship to you, and you won't need a big plane from UPS to ship the good. You're not completely stopping the reliance on third-party shippers, but you're relying less on third-party shippers to ship the good. And so that's what locating closer to consumer does. Okay, that's the benefit. Now, so you don't necessarily make things faster by locating close to consumer. And this is one thing that we show in the data. It's very clear that if you have a warehouse close to you, it doesn't mean you get the good faster. Okay, because what Amazon did in 2006, 2008 is to guarantee 2-day shipping for everybody. Okay, so what it does is that you're lowering the cost of providing 2-day shipping. So the channel is not through the demand, the channel is through cost. It's cheaper to provide a 2-day shipping guarantee for everybody by locating closer to consumers. Okay, that's the benefit side of the trade-off. The cost side of the trade-off is that by having a very dense network, you're not realizing these economies of scale at managing a distribution center. Okay, so you want a distribution center to be very big because there's big economies of scale of having the robots, piling on and moving the box and stuff like that. Okay, so you're losing scale by having many smaller distribution centers, and then this is where the tax comes in. The U.S. has a very funky tax system where up until 2018, you don't pay sales tax if you don't have physical presence in the store. In the state where the demand is. Okay, so that's what Nexus tax laws made is, technically it says retailer had to have sufficient physical presence in a state to collect taxes. So this was implemented when catalog were very important in the U.S. Okay, but for when online retail became popular, it gave a big cost benefit for Amazon and other online retailers because you can locate only in Kentucky, right, and ship to California and not pay tax in California. Okay. So why does that matter for the trade-off? Well, it's going to reduce the incentive. So the first part means that I should go in California right away. That's where the largest market is. But if I go to California, if I open one warehouse in California, suddenly everybody in California is taxed. And that's a huge decrease in demand. So that's going to be the analog of cannibalization in the Walmart paper, is that I don't want to locate closer to consumers, because if I load too close to consumers, tax go up. Okay, so here's what we do in the paper. First, we quantify that trade-off to infer something about these economies of scale. Because there's two types of facilities. Okay, there's two layers of the vertical chains that Amazon is entering. So we're going to quantify first the reduction in what is the cost benefit of locating closer to consumers, okay, bypassing UPS. Okay, and the other thing is that by opening your own sortation, you're doing sortation in-house. Okay, but it's effective only if you co-locate facilities, as if you locate a sortation facility next to a warehouse. So we're going to quantify the cost reduction coming from that in-house sortation. And so that's going to be the two sources of economies of scale in this market. And then we're going to quantify the impact of the policy. How does the tax policies distort investment? Okay. So I started at 9. Very good. Okay. I'll try to speed up a bit. Told you I was speaking very slowly. Okay, dynamic problem. Okay, so again, very similar to the Walmart case, the way it's set up. So I'm gonna take as given the number of facilities that Amazon enters every year. So there's an outer maximization that maximizes over how many stores to open in 2008, right? I'm going to take that as given, and then choose to, given that I order 20 stores today, where to place those 20 stores, okay? L is going to be the location of a given store. I'm also going to take as given the size of each of the stores. I keep saying stores, fulfillment centers, okay? And then I'm going to choose where to locate those facilities and where to locate the SCs, the sortation facilities, okay? Now, one thing that is, gave us a few headaches here is that when you look at Amazon's expansion, there's a lot of co-location, okay? So you see that if you drive by the highway here, often you're going to have two giant Amazon fulfillment centers almost, adjacent to each other. And that's, because of capacity. So they add one facility, and then they rent another big space, and they add more capacity. And so we're going to think of that as like capacity expand. When you co-locate, we're going to think of this as like adding capacity to an area. Okay. The dynamic control is going to be where to locate the facilities, and the action is going to be the sequence of where to locate each of the type of facilities. And you're maximizing this discounted sum of profit, taking as given the number of stores of each type, number of facilities of each type that you're opening.
Should I think of locations as discrete or in some continuous?
Here it doesn't matter because I'm going to swap. So I'm going to take those locations. But when I get to the counterfactuals, I'm going to assume it's discrete. I'm going to define a grid and Okay, so here's the profit. So revenue is going to be coming from demand. I'm going to assume that Walmart has a constant markup. Okay, so that's new bar. I'm going to take this from their financial statements. Part of this is that Amazon sells millions of things. I don't want to deal about demand for individual product, okay, or markup on individual products. Okay, so that's going to be coming from the demand. That's coming. The shipping cost is where a lot of the action is, okay? So I is a location of a consumer, that's a county. L is the location of where the facilities are. Demand, this is the number of orders from a given county, given the network, okay? The network affects demand through taxes here, right? That's where that's the relationship between investment and demand. And this guy here is how the distribution takes place within the network. So it's an origin destination probability of the probability that the order gets fulfilled from the order to I gets fulfilled by location L. Okay, so I'm not going to show you the equation, but we're thinking of this as a little bit like there's a probability that the good is available in each of the locations. So condition on the good being available in the closest location is going to be fulfilled with probability 1 from the closest location. If it's not available from the closest location, then it's going to go to the second, and then there's a probability, is an ID probability that the good is available in that second location, and all the way like this. And so you can construct a probability like this. And where capacity shows up, I mean, I told you that there's a lot of co-location. It's going to affect the probability that the good is available. So if you have more capacity in a given area, you have a higher probability that the order is fulfilled by the closest facility. Okay, so that's where that is. And then this is the shipping cost. So shipping cost is a function of the distance. Okay, and so that's what we're trying to measure. The benefit of density, the benefit of locating closer consumers. That's my theta d. And then the benefit of vertical integration. So this is a dummy, whether order I fulfilled by location L, okay, is an in-house sortation. Okay, so that's equal to 1 if this facility L has a nearby sortation center. So if if the order is fulfilled by a location where there's no sortation in the area, then you don't have this benefit. But if there's a sortation facility nearby, let's say it's a Milwaukee warehouse and there's a Milwaukee sortation and the order goes to Chicago, then it's a lower shipping cost. Sounds good? Good. And so we're estimating these two parameters, and then the fixed cost is going to be a function of density. Again, it's expensive to locate downtown LA or something. Yep.
So in the shipping costs, you not, because you have the decision of like shipping through your own center or shipping through like UPS or FedEx.
Yeah.
So isn't it, can you also think of it as a problem of like, oh, I'm going to build my network to alleviate the bottlenecks in the current system? So it's more talking about like, the strategic plan isn't really to try to distribute most efficiently, but to substitute from the bottleneck or away from the bottleneck system. So maybe it's not even a density problem, where just that like the postal service is maybe overdeveloped in Amazon purposes in kind of low density areas. So because of that, they have less incentives to kind of create facilities there. So I mean,
so I wish we had better data to dive into these things. In some ways, there's going to be a giant reduced form that tries to capture these things. But yeah, I think that's what's going on in the background. Basically, it's, Mara was talking about peak load demand and how it measures. And that's the same thing here, is that, the cost of using UPS is very small in most times, but at Thanksgiving, it shoots up. And so the reason you want to have this kind of dense network, even though you're not using your facilities all the time, is because you want to make sure that you meet your same-day delivery or two-day delivery, even during peak demand. And UPS is not going to say, I have an Amazon-only plane, or I have an Amazon-only route, right? There's a specific investment, and they won't do that. So in the background, that's where this is, but I cannot open this box. I don't have data on that. But I think this is a good avenue if you manage to get your hand on how long, which route goods take, and you can get that by scraping Amazon orders, perhaps. But okay. So now I'm going to go through these things. I'm going to go fast because I want to talk a little bit about how we estimate these. But the first thing to do is to estimate these. Okay, that's important because this is the downside of density, is through the tax, right? So I want to know what is the effect of entering early in California and jacking up the tax. Okay, that's going to be the main side of the negative side of the trade-off. So here we're using a CS demand curve, demand function, so very simple. So data, I didn't mention the data. The data is from ComScore, so it's a survey company that installs cookies on your computer and then stores all your browsing history, everything, including your Amazon purchase and everything. okay, and all your online shopping. So it's a very selected sample, so we have to do a lot of messaging to extrapolate and get a county level demand, but it's the best data about Amazon demand. I don't know of any other data that gives you where people shop and how much people shop given where they live. Okay, so this is that. Now the demand is you either buy offline. This is the outside good. You buy at Amazon. You buy at a taxable, like Walmart, taxable online retailer, or non-taxable online retailer. Okay, and so we're trying to estimate this this parameter sigma. So all these sellers are selling a continuum of goods. Okay, and so to make things tractable, because again, I don't want to think about TV versus cat litter. Okay, so the price of a variety, I'm going to assume, is taking this nice form. This is kind of the willingness to pay or the quality of this variety. And I'm going to assume that the price is just multiplicative. So there's a price index for the platform. So Amazon can mark up each of these prices. And so this is kind of the price index or the price of Amazon versus Walmart online and stuff like this. Okay. Now with the magic of CS, you can write down an expenditure share, including the tax. The other thing I want to mention is, this is we're not really going to use the price really. We're going to use expenditure share, but we need some kind of price variation to identify the demand elasticity, and the price variation is coming from the taxes. Okay, so that's because the price is separable in the tax. That in the log form is going to be that the expenditure is also separable in the tax. Okay, so you can do the CS algebra. You're going to get this kind of equation where you get an intercept, the price index, the tax effect, and the price elasticity is going to be the slope of the tax here. Okay, and the nice thing is that we have a lot of variation in tax because of the staggered entry of Amazon, right? So Amazon enters, in Pennsylvania. Well, the people next door to it, can get the good, because they're also located close to a fulfillment center, but they don't pay the tax, and so you have this discrete treatment of having the tax or not. And then this is the variety. This assumption gives you this variety index that's going to be absorbed by a fixed effect. So this is how many goods is available on the platform and all of these things. Okay. So we're turning this into a fixed effect regression, a lot of fixed effect to capture the fact that we don't really see the price and we don't really have good measures of the variety. All of that is going to be absorbed by fixed effects because the same good and the same prices are available everywhere. Amazon doesn't discriminate based on where you live. Okay, that's very nice of them, and very nice for us. So we can absorb all of these things by platform year fixed effects. And then to get the price of the outside option, we're going to try to use county and county trends to capture these things. Yep.
From the Nexus loss, we would expect that a lot of these fulfillment centers are located right on the border.
Yep.
Another state, right? Did you ever? I don't remember if you gave the
Yeah. Yes, absolutely. You see that, and it's very clear. Like if you look at Nevada or Arizona, very clear. Yeah. Okay. Demand elasticity 1.5. Okay, I don't know. Seems reasonable. It's similar to the ENAV papers and other papers that I've looked at online demand. But the elasticity is important. Again, it's going to give us the cost of entering early in the state. Okay, that's the main thing. Now the cost function. This is the cost given the network, shipping cost, labor cost, and fixed cost. Labor cost is the main variable cost except for shipping. And so the labor cost here, we're going to assume I took it out, or maybe I showed it earlier and I forgot to mention it. So there's going to be a labor demand, where given the quantity, there's economies of scale, in the facility. And so given the number of units, there's a Cobb-Douglas function that tells me how many employees I need to hire. Okay. And this is the wage in the locale. Okay. Now, a really important parameter is this stockout or this origin destination kind of logistic function. We don't have data where the good ships. Okay? What we know from the demand is where demand is originating, right? And we know where the facilities are, okay? But we don't know where the good is, who ships to what, okay? So to identify this, what we're using is that we have data, bad data, but we have data on the number of employees at each facility, okay? And so assuming this kind of very flexible labor demand, okay, the number of employees in a given facility, given its size, is proportional to the number of orders that they're processing. Okay, so we're going to do a non-linear least square estimator where we know where demand is coming from, and we know how many employees are each facilities, and so we have one or two parameters in here that minimize the distance between those two things. Okay, so that's where we get the logistic parameter. We do find that there's economies of scale in each of these facilities. Then the remaining parameters are these ones here that relates to the logistic. Okay, so let me go back to the inequality that I started with. So what I see in the data is a diffusion pattern, right? So I see the rollout of the network, that's A star, that maximizes, under perfect foresight, that maximizes this function. Okay, so again, you know, the finite dependence means that I can swap the entry date of different facilities, right? I know that Amazon entered in Arizona first because they didn't want to pay taxes in California. As demand increased, eventually they entered in California. Okay, and so I can swap these kind of things. Okay, so I can swap Arizona for California. Now I don't have as many openings as we had in the Walmart example. So there's about 130 facilities total. So we end up using about 5,000 swaps by looking at all these swaps. Okay. Okay. Now, this is where, if you assume perfect foresight, this is this. As I said, this is a very deterministic model. If you write down these inequalities, okay, they're going to be all violated. Okay. There's no way these inequalities are satisfied with this model. Okay. So you need to add something, and we talked about, you know, these things earlier in the week. So we need to have something to rationalize the data. So here what we're saying is, okay, and this is borrowed from the Tom Holmes paper. So we can measure this part here. So I guess I should have used a slightly different notation. So I can measure, you know, I have a model for the revenue function coming from my demand, coming from my logistic model, right? That I can calculate one side, those trade-offs from data, but I know that that model is very imperfect, right? So there's measurement error coming from the fact that I'm estimating demand, true demand, and then there's other things that I don't see that Amazon condition on when they make those decisions, okay? So I'm going to add a shock to this, okay? It's not very micro-founded. It's better to think of this as measurement error, okay? But it's going to be a residual that rationalizes the fact that if I calculate all these 5,000 swaps, none of them will be, or very few of them will be rationalized. Okay, there's going to be a lot of violations. I mean, most of them will be satisfied, I hope so, but not all of them, right? So you need some kind of error. Now that complicates the estimation here because I need to find a way of, I cannot use individual swaps here because there's an error that I don't see. Okay, so I need to make an assumption about what these errors are. And so if you expand, remember the profit functions are linear in the parameters. So this is going to be the change in discounted variable profit from swapping Arizona and California, right? The change in distance, discounted sum of distance, and fraction of orders that are vertically integrated orders, stuff like that. Okay, that's what these axes are. Here's the assumption on the error. So I'm going to assume that the error is independent of the observed predetermined difference in the profit that enters these things. Okay, so here, another way of saying this includes changes in revenue. This is include changes in demand. Okay, there's a lot of errors in calculating these things. Okay, so but there are components in this that are deterministic. You know, where the for instance, the population of those areas. Right? If I enter in California, I know that California is much bigger than Arizona. Okay, so the population of these states is deterministic, and it's pretty much known at the beginning in '99. Okay, the source of the error is estimating demand in Arizona and in California. That there's a lot of errors there, right? But the big component of demand is how many people live there, right? Or the population density, or and stuff like that. So that's what I mean by predetermined variables. So there's a lot of predetermined variables that can predict change in y, change in x. Okay, I'm going to assume that the error, the measurement error predicting the revenue trade-off, is independent of those kind of predetermined components. Okay, so I'm going to tell you exactly how I'm using it in a second. But given this assumption that there are predetermined variables that I can use that predict this, I can construct a set of moments, or we can think of it as instruments, okay, that allows me to average out these errors so that their mean 0, and then I can construct a moment inequality. So let me just go back a tiny bit. So I told you, there's a lot of possible swaps I can take. None of them will be satisfied because of the presence of the errors. So you cannot build an estimator based on this, you cannot just do a nonlinear least square where you're trying to minimize the violations, because each of them will be, there's errors that, they're not going to be, satisfied. But what you can do is average out, if you can find proper instruments, you can average out across swaps, across different options, so that on average this guy is 0, and that's where the instrument is important, just like what you do in GMM. So on average, the model is going to be right at predicting the swaps, or the order of entry. It's not going to be correct at each of them, but when you average out across different decisions, this thing disappears, and on average the model is correct. Okay, so that's kind of the logic of the moment inequality. But I need to find those z's. I need to find instruments or moments that allow me to do this. Okay, did you want to ask a question?
I'm trying to get a sense of how these errors compare to kind of like a multinomial loaded model, where I'm doing a discrete choice over all these different things.
Yeah, I don't want you to think about it this way. That would be, yeah.
Would that be a super messy approach to the problem?
Potentially, I have no idea how you would go about doing this. Yeah, we can talk about this later, but yeah, I don't think it's a good idea to think this way. Think more measurement error. Okay, so how do I construct those z's? Okay, very much like when you do IV regression. Okay, I want to find shifters of the trade-off that predict the trade-off. Okay, that for each swap, let's say I swap California and Arizona, I cannot use the realized difference in profits between swapping these things, because that's endogenous. There's measurement error in there, but I can use predictors of whether the delta y for California and Arizona is positive or negative, and then predictors whether the distance is going to be positive and negative. Okay, that's kind of the idea of the z. So here in the literature, most of the time the z's are discrete. Okay, so we're going to essentially group. We're going to have we have 5,000 swaps, and so I'm going to take subset of these swaps that shift the trade-off in directions that gives me an upper bound, and shift the trade-off in the directions that give me a lower bound. Okay, that's kind of the logic. Okay, so I'm going to group the swaps, or the pairs of decisions based on predetermined shifters of revenue and distance that allows me to predict what the actual change in y and the actual change in x is. So it's kind of the relevance condition and when you do IV regression, okay? So those predetermined variables are going to be population weighted average taxes between the two states. Okay, that's going to be a big shifters of revenue. Okay, predicted average, population weighted average wage and rents across states. So essentially I'm using population to avoid using revenue and demand. Okay, and then same thing. So I'm going to use population average distance. You know, if I look at it in California, population weighted average distance is going to be quite low, right? It's going to be a big decrease in distance, okay, in population weighted average distance, okay? And same thing here, so for facilities, and the fraction, change in the fraction of consumers that would be benefiting from vertical integration between two possible swaps, okay? Okay, so I have 5,000, a little bit more than 5,000 swaps, okay? And I'm selecting them based on, I think there was a question early, so I'm looking at swaps that are, you know, at least a year apart, okay, that have the same type. I don't want to swap NFC for an SC, so it's within type. And then, you know, I'm going to look at swaps that are very similar, similar sizes. I don't want to swap a really small facility with a really big facility, okay? So here's kind of an intuition of how this thing is identified. So here's one example of a grouping. Okay, so I take swaps that satisfy these conditions. Okay, so J is the choice that I made. So I'm swapping two facilities, J and J prime, and delta X prime is the change in distance from the chosen network to the counterfactual network. Okay, so swapping J for J prime it gives me a reduction in distance, meaning that the choice of network was closer to consumers than the alternative. Okay, and I'm gonna look at, you know, the set of swaps that gives me reduction. That means where the choice is closer to consumers, right? And at the same time, those swaps give me increased taxes. So this is like swapping Arizona for California. Okay, so the vice versa. So the Arizona was chosen. Amazon could have chosen to locate further away, right? But by locating in California, it increased its tax, located closer to consumers. Okay, so just like my little example at the beginning, this is going to give me a lower bound on the thing. Okay, but you know, because of the measurement error, I'm not actually comparing actual changes in distance or actual changes in revenue. So this is going to be an informative bound if the predicted revenue conditional on being in that group is negative, and the predicted change in distance is positive. One is negative, one is positive. Okay, so it's relevant. Okay, and so here's an example of the tax swaps. So you can do the opposite for getting an upper bound, but for the lower bound, let's say I'm looking at the average change in revenue conditional on satisfying this condition. Okay, and the average change in revenue condition satisfying this condition is negative. So it goes in the right direction. So I'm looking at population average change in distance, population average change in taxes. It does lead to actual reduction in revenue. Okay, when I enter in California. And then same thing, if you look at the X, it also leads to a reduction in distance. So you're looking at California instead of Arizona, lower revenue, lower taxes, lower distance. Okay? If you take the ratio of these two things, that gives you a lower bound on the travel cost, on the shipping cost. Okay? And you do the opposite, it gives you an upper bound. Now you can do swaps based, instead of taxes, you can do wages. You know, there's a similar trade-off here that, you know, if I locate in a high wage area, I'm locating most likely close to consumers, right? Because urban areas have higher wages, right, or higher rents, but I'm locating closer to consumers also. So there's a similar trade-off there that gives you slightly lower okay. So this is just summary stats. Okay, this is not quite an estimator, when you put all these moment conditions together, okay, so I'm running out of time, so I'm going to skip the econometrics part of the talk. Sorry, okay. But basically, there's a lot of groupings here, right? Now, if I'm looking one by one, I can kind of look at this kind of calculation. I want to create a big GMM estimator out of this, okay? So there's many moments here that I'm using. And combining all of them together, that gives you a moment inequality estimator. So here we're using a moment inequality estimator coming from people like Bogny and Xiao, who's right upstairs here, to calculate bounds on, or confidence intervals around the parameters. Okay, it's a computational thing, so I said, oh, I'm going to show them an algorithm. Everybody's showing algorithms. Here's the algorithm. That's fine. These are the estimator. They are the estimate. So this is the estimate. There's a very simple univariate estimator where you only estimate the distance parameter. Here I'm using 4 moments. So essentially taxes and input price, varying distance. Okay, that gives you an estimate like this. Now it's actually lower than when you start conditioning all other stuff. In part because what you're missing here is the trade-off when you locate close to urban areas. The fixed cost is, the fixed cost of operating is quite big. So once you start conditioning on the fact that fixed costs are much higher in urban areas, you're actually underestimating the shipping cost. And then this is actually overestimating, because part of the reason you locate close to consumers is also to realize the vertical integration aspect, so the ability of integrating and sorting. And so when you put those things together, you're able to more realistically decompose the benefit of density into these 2 parts. So you're getting a negative number here, so there's big benefit of vertical integration, and there's big cost savings from locating close to consumers. Okay, so this is just raw prediction values of this economies of scale effect. Okay, so as the network was expanding, what you see is the average shipping cost. It went from about $2 per box to 50 cents per box, or sorry, to 29 cents per box. Okay, if they did not invest in the in sortation, so they didn't do the last vertical integration thing, their fixed cost would actually be 50 cents. So quite a bit of that reduction is due to vertical integration, not just density. Okay, the actual variable cost is going down a little bit slower because there's a trade-off, right? So remember that if I just want to minimize shipping costs, I want to have a very dense network. But if I have a very dense network, every facility won't be used at capacity. So the variable cost is going to be higher of using each of them. And also the fixed cost is going to be much higher because I'm locating in expensive areas. Kentucky is very cheap to build warehouses. Okay, this is my favorite graph. When I teach 101, I always teach about long-term average cost curve versus short-term average cost curve. Okay, and so each of these lines is a different technology, so it's a different network. Okay, and so the lower envelope, if you think about this as a static problem, as demand increases, you want to go to the lower envelope. And so the red curve gives you this long-term average cost economies of scale that I was mentioning. So each of these things has lower as economies of scale, but as demand increases, you want to shift the technology down and have a larger scale. Okay. Now, I'm going to take a little bit of time for the counterfactual, just a tiny bit. So then we want to know, how does the tax system distort investment? Okay, the distortion we're thinking about here is that it took about 12 years for Amazon to enter in California. Okay, that's like the starkest example. They kept piling up facilities in Washington, in Oregon, and then Arizona and Nevada to serve California. Okay, so that's very inefficient because you could have realized these economies of density sooner, but because of the tax, you didn't do that. Okay, so that's kind of what we're trying to do. Eventually, the regulation was scrapped. So there's a Supreme Court judgment in 2018 that eliminated Nexus tax laws. okay, how do we solve this? So I told you the model is complicated, and so I cannot solve the dynamic model. Okay, so everything I'm going to show you is, just approximation based on a static model. So I'm going to ignore the option value of adding more and more investment. Okay, and I'm going to solve the problem as if it was a static problem. For every year, given the state of the demand, where do I locate the facilities and how many facilities to locate? It's still a really complicated problem because, there's what I'm doing is I'm discretizing the set of locations. I'm assuming there's 250 possible locations. And now, because I want to look at the effect of taxes, I don't want to hold fixed the number of facilities. I want to know if I raise the tax, how many fewer facilities are going to be built. Okay? So it's a really big combinatorial problem, like where to place and how many locations. So, and so even the static problem is very hard to solve. Now, maybe Fedor and Bertel has better ideas on how to solve this. What we went to the OR literature and came up with this paper, which, I don't know, it was a very good idea, we thought, so we used it. So it's a genetic algorithm, the simulation-based genetic algorithm that kind of solved this kind of problem via simulation. Okay, here's the algorithm again, but the intuition is very simple. So part of the problem of solving this very discrete problem is that there's way too many combinations. Like if I can solve the problem in 2006 by just enumerating all the possible locations, and then there's only 4 facilities or 5 facilities that maximize profits. So I can look at all possible combinations of 4 or 5 facilities. But the minute there's like 20 or 80, I cannot enumerate all possible locations. Okay? So the discreteness becomes really complicated. So what this particular algorithm does is that it kind of convexifies the problem by trying to solve for the probability of entering in each of the locations. Okay, so you start, and then because it becomes continuous, I can use like a hill climbing type algorithm to make progress on the probability of entering in each of the locations. Okay, and as I go through the iterations, these probabilities would shrink to zeros and ones, and then the network will stop there. Okay, so that's what this particular algorithm does. It combines a genetic algorithm where you can perturb those probabilities to try different solutions with a hill climbing thing where you're shrinking those probabilities to zeros and ones. Now, this is, of course, going to get stuck in the local solution. Okay, so you don't want to do it once. You want to do it like 10,000 times. So here we have a very nice cluster here. And so, I requested like several thousand nodes, but they don't need to talk to each other. So you just, launch the job with different starting values, that will give you many, many possible solutions. And then you just take the max. And so what I'm presenting to you is the best of those for each of the years. It's probably not the global max, but, promise I tried. Okay. These are the locations, so predicted FC locations. And you can see this idea that with the tax excess laws, you want to locate in adjacent states early on. As demand increases, at some point, the benefit of entering California outweighs the tax effect. And so suddenly you enter one. Once you enter one, then you turn on the tax, so you might as well entering a lot in California. And so that's kind of what happens here. Okay, and you see the same thing kind of, Amazon use Milwaukee a lot. Okay, Amazon, to fulfill demand in Illinois, it piled up facilities in Milwaukee, and so that's why you see here. Okay, without taxes, so if you don't discriminate, if you say everybody, the tax is not function of where you are, suddenly you don't see facilities in the desert, right? It doesn't make any sense to have facilities in the desert of Nevada. And so these facilities, Amazon opened right away in California, right? And of course, as demand increases, there's more and more facilities in California. And so then you have a map that looks a lot closer to what that Walmart map looks like. You right away want to locate where demand is. And so you can see the distortion here by looking at these two networks, these two counterfactual networks. This is the distance to consumers. So it goes down over time, but it goes down much faster without the tax distortion. Okay? But it could have, the problem with taxes is that it lowers investment incentives, right? That's always the problem with taxes. And so you see that here, the number of facilities is lower. Sorry, yes. Anyway, I forgot about what I was going to say. Anyway, forget about that. Just distance. So you do see that with the tax nexus laws, the shipping cost decreases but remains like this, and then without the tax distortion, you see lower shipping cost. Okay. Here's the final slide. So what is the welfare effect of eliminating tax distance laws and having uniform taxes? Of course, Amazon's not happy with this because you're kind of taxing Amazon more. And so there's a large decrease in profit for Amazon, but it benefits two other parties. So other firms benefit a lot because you eliminate the tax advantage of Amazon. So rivals' revenue increases. Consumers are not happy, but then the governments raise more revenue. So there's missing revenue from this. And so here are the fiscal multipliers that you would need to assume such that eliminating tax nexus would break even. Because if you think that the tax multiplier is higher than this, then the welfare effect goes one way. If you believe the tax multiplier is the other way, but this is the tax multiplier you need to believe for the eliminating tax nexus to be a good policy. And when I Google fiscal multiplier in the PF literature, they seem to agree that this is a good tax multiplier to use. So it does seem that eliminating tax nexus is actually welfare improving in this particular context. Yep.